can say that these two triangles share this segment GI, this diagonal. And so I have these two triangles right here. I got this guy, and then I have the other one below it. And these triangles are congruent because of angle side angle. And that will always, always work for any parallelogram. You draw on the diagonal, it's going to create these two congruent triangles. Now, having that little fun piece of information, it says each diagonal of a parallelogram divides the parallelogram into, that blank would be two congruent triangles. That is part 3, it's item 3. The blank, they didn't give you much space for it, but it is two congruent triangles. But these two congruent triangles are going to tell us a lot about these parallelograms. Because I have proven that this red triangle is congruent to this green triangle, I've got 3 other corresponding parts that I originally didn't know anything about, but I now know that they're congruent because I know the whole triangles are congruent. I'll feed you baby birds. So we knew that that was parallel to that, and this was parallel to that. Now that I have shown that these triangles are congruent, yes, we found those alternate interior angles, and that was wonderful. And yes, they shared that segment. But now that I know these two triangles are congruent, well, this segment here, segment GA, is congruent and corresponding to this side here. This segment here, DG, is congruent and corresponding to that side there, segment AI. Because within those two congruent triangles, those are corresponding parts. So what have I just shown about parallelograms? The opposite sides not only are parallel, but they're also congruent. That will always, always work. This is one of the properties of parallelograms. So your opposite sides are congruent. This angle here, angle D, is congruent and corresponding to this angle there, angle A. And we didn't originally know this stuff. This is just because we proved the triangles are congruent by angle side angle. So, what do we just see about opposite angles in parallelograms? Those are also congruent. So I'm looking at item 4. Part A says opposite sides of a parallelogram are congruent. And then part B, opposite angles of a parallelogram are congruent. And some of you may be thinking, well, how do we know that angle G, this whole angle, is congruent to this whole angle I? We can't prove that right now. I would agree with you. However, what if we drew in diagonal DA? Then we would just prove that this triangle over here is congruent to this triangle there, and then those would be corresponding parts. So remember that you have both diagonals to prove. So yes, opposite angles of a parallelogram are congruent. Prove the theorem you completed in part A. Use the figure in item 3. So if I had to prove that, you would prove that these two triangles are congruent. So triangle GDI is congruent to triangle IAG by angle side angle. And again, where did those 3 parts come from? The 2 angles were the 2 different sets of alternate interior angles, and they shared this side GI. So you have to know how to get here. So I'm going to put a little asterisk here and say you can't just come out of the gate swinging saying, hey, triangles are congruent, as I said so. Like, you better be able to work here. And that is because they share segment GI, and then you have those 2 different sets of congruent alternate interior angles because their opposite sides are parallel. So you're eventually going to get here. So that these 2 triangles are congruent. And so if I am, and then from there, proving that opposite sides are congruent, let's just CPCTC. Once I have that these triangles are congruent, then I know that segment DI is congruent to segment AG by CPCTC. Those triangles are congruent, and that means all of the other parts must be congruent as well. And then I have segment DG congruent to segment AI. And again, that same thing, CPCTC. Then if I wanted to prove the other theorem, that the opposite angles are congruent, so if I want to show that angle D is congruent to angle A, those guys, again, CPCTC. That's it. Again, showing that angle G, the entire angle G, and the entire angle A, those two opposite angles, if I wanted to prove that those opposite angles were congruent, I would have to draw in the other diagonal DA, and then do that whole process over again. Prove that those two triangles are congruent by angle side angle, and then I can do CPCTC, but I don't think we need to go through it. Alright, so that's page 213. Whew. On page 214, it introduces a new word to us, corollary. It says, explain why the theorem in item 4 can be considered as corollaries to the theorem in item 3. If you look over to the far left, it says a corollary is a statement that results directly from a theorem. So the theorem in item 3, what did it say? Hold on. It said that when you draw the diagonal in, each diagonal divides the parallelogram into two congruent triangles. So that was a theorem, and then from that information, from the fact that we had these two congruent triangles, we just took that and ran with it and said, well, if that's true, then this is true. If that's true, this is true. So all of those statements that we said were definitively true and proved, those all came directly from that previous theorem. So those could be considered corollaries. And corollaries, again, are just something that follows from a theorem. It's just common sense. For these problems, we don't have time to go over every single one of them, but I do want to quickly talk about part C in item 6. It says solve for x and y if you know the length of segment KL is 2x plus y. What? Oh, okay. And then the length of LU is 7, and then the length of UC is 14, and the length of KC is 5y minus 4x. So there's some equations that we can come up with that would be true. For instance, the length of segment LK is equal to the length of segment UC. That's a true statement. So when I plug in these values, these expressions, I get that 2x plus y is equal to 14. Can we solve this equation right now? Why not? Two variables. We don't know how to solve one equation with two unknowns. So if we have two unknowns, we need two equations. So we're going to have to use this other piece of information that the length of KC is equal to the length of LU, because opposite sides of parallelograms are congruent. If segments are congruent, then their lengths are equal. So I'm just going to do a little switcheroo here. I'm going to put the x term first. So I've got negative 4x plus 5y is equal to 7. So what have I got here now? This is a systems of equations. So this is algebra 1, systems of equations. You can either use substitution or elimination to solve this. I think the easiest would be to use substitution. If you notice, your x terms already have opposite signs. That's good when you're trying to use elimination. So if you can make this coefficient in front of the x term in your first equation to a positive 4, then when you combine the two equations, those would eliminate. They would cancel each other out. There's 0 pair. So what I'm going to do is I'm going to take this entire first equation and multiply it by 2. Just multiply it by a scale factor of 2. When you do that, you got to multiply every single term on both sides of the equation by 2. So I'm going to get that this is 4x plus 2y equals 28. This is my new equation. Now I'm going to combine these two. If you want, you can put a big old plus sign. So negative 4x and positive 4x, that's a zero pair. Those are going to cancel out. So I get 0 plus 5y and 2y gives me a total of positive 7y. And then 7 and 28, that gives me positive 35. Well, 0 plus 7y is just 7y. So now I have 7y equals 35. Divide by 7 on both sides, and we get that the y variable is equal to 5. Once I've got that, plug it back into one of your original equations. So I'm going to have that 2x plus 5 is equal to 14. Subtract 5 from both sides, 2x equals 9. Divide by 2, x is 4.5. So I just want to refresh you on systems. Substitution or elimination. But yeah, systems of equations. Okay, moving on to more properties about parallelograms. This is the last thing that we're going to talk about. The theorem states, this is right above item 7 on page 214. The theorem states that the diagonals of a parallelogram bisect each other. So these parallelograms have got a lot of properties. A lot of things that you have to know about parallelograms. Both pairs of opposite sides are parallel and congruent. You've got your diagonals that form two congruent triangles. You've got that your opposite angles are congruent, and now the diagonals, they will bisect each other. So, they're expecting y'all to rewrite this as an if-then statement, and then do a two-column proof in its entirety. That means create your own diagram, write the given statement, write the proof statement, and then go. And then prove it. So I'm going to get y'all started. It says to rewrite the above theorem in the if-then form. I hope that that we're comfortable with this, but I would write it as this: if a quadrilateral, just put quad, abbreviation. If a quad is a parallelogram, pretty much saying if you've got yourself a parallelogram, then the diagonals will bisect. The only thing that you can assume, or the only thing you can start off with, is that you've got yourself a parallelogram. Oh, that says so she's not here. Alright, so let's keep going. So we got the if-then form. So let's get a diagram going. So we've got that, we have a quadrilateral here. Has to be a parallelogram. That's the only thing we're allowed to assume. So we know that's parallel to that, and that's parallel to that. We're going to call this A, B, C, D. We're talking about the diagonals, so we should probably draw those in our diagram. So we have one of the diagonals, AC, one of the other diagonals is BD. These are eventually going to intersect, obviously. When two segments intersect, they intersect at a point. We'll call that point M. So we are given parallelogram A, B, C, D. That's the only thing that we can start off knowing, is that we have a quadrilateral that happens to be a parallelogram. And by definition, both pairs of opposite sides are parallel. So that's all we can assume right now. What we're trying to prove is that these diagonals bisect each other. So what our proof statement's going to look like, I have to show that segment BM is concurrent to segment DM. So that's one thing I have to show.